Now, how do we trace things back in time? I showed you we had, since 1610, we've got one of the longest duration measurements of the sun or any climate, direct observation of something relevant to climate by measuring sunspots. Well, I've got these different measurements, and I'll explain in a little bit the variations between all of them. But we have about a dozen different experiments, spacecraft, that have measured the output from the sun. And luckily they overlap, which lets us take care of some of these offsets. Lets me put together one nice composite of what the total irradiance should be, and then I can correlate that to sunspot number here. And I can say, okay, I understand how the total irradiance is linked to sunspot number, and I've got a 400-year record of what the sunspots are, so I can kind of guess what the sun has been doing for the last 400 years. Plot that up here. Then you can make some other assumptions. Maybe the output from the sun doesn't just depend on the number of sunspots. Maybe it depends on the average for a time, or the length of these sunspot or solar cycles. Or so people have made different models that say that when the sun is less active, like it was back here in late 1600s, that it would be putting out less total energy as well. So we have several different models for how the sun may have been changing on long durations, long enough that they could affect climate. So we have some history of what the sun's been doing. In the late 1600s, to study climate, you may have heard of something called the Little Ice Age, a period, 50 years or so, where Europe was a lot colder. Winters were harsher and longer than usual. People were having parties ice skating on rivers and ponds that weren't normally frozen. If you study the sun, you know this is the Maunder minimum, a time for 75 years when there were very few sunspots. Jack Eddy in 1976 linked the two of these and published a paper that got people thinking a little bit more. This Maunder minimum period in the late 1600s, when there were very few sunspots, corresponded real nicely with the Maunder minimum. And it wasn't that people got bored of sunspots and quit looking for them. They were actually looking real hard because sunspots were so rare they didn't want to miss any if there were any. So we do have good observations this year. There just really were very few sunspots for a long period of time. The sun was probably a little bit cooler than it normally is, and temperatures, especially in Northern Europe, were colder than normal. Here's a plot showing temperature of the Earth. This is globally average temperature for the last 150 years here. And different regions where we have measurements of temperatures on the surface of the Earth. The bottom plot being the difference between the early 1900s and the mid-1900s, where brighter or red colors mean things are getting hotter. The upper plot is the difference between the mid-1900s and about 2000. You can see that we've got things to be a lot warmer, especially across the northern hemisphere, Northern America, Northern Europe, and Russia, in the latter part of that century than in the earlier part. We can take those temperature records back in time. Again, with proxies, we don't have direct measurements of temperatures. And what we'd really like to know is how much of temperature changes are caused by humans and how much are caused by natural things, things that we can't regulate. How much, for instance, is due to the sun? There are a lot of things that cause climate change. I talked about the sun a little bit. It's one natural forcing or cause of change of climate. The other one is volcanoes. If we have volcanic eruptions, they can put up enough dust, sulfates, to block some of the incoming radiation from the sun and cool things off. There are some natural oscillations in the Earth. We've heard of El Nino, different circulation patterns in the ocean. It can change where warm and cold water is in the ocean. There are land cover changes. How we deforest places will affect how much energy is really absorbed down on the surface of the Earth. And anthropogenic forcings, atmospheric greenhouse gases, things that we can be putting into the atmosphere. All of these can affect climate. Here's a plot, and the black shows globally average temperature on the top for the last 30 years. The orange is a model, a fit to that, where I try to break down what causes those temperature changes into a few of these kind of fundamental components. The sun, shown here with its 11-year solar cycle in green. Volcanoes. Pinatubo was a big eruption in 1991. It caused a decrease in energy that was allowed into the Earth's atmosphere. El Nino in purple, and anthropogenic effects, increasing greenhouse gases and other atmospheric effects. But combine all of these up and you can do a reasonably good job modeling what the temperatures are, globally average temperatures of the Earth for the last 30 years there. I can even extend that record back further in time. This is going over 100 years now, where anthropogenic effects weren't so large early on in the 1900s and then increased here. But again, you do see spikes due to different volcanoes with the 11-year solar cycle. And you can do a reasonable job of fitting the temperatures like we do on the top here to figure out how much of temperature change is caused by all of these different effects. What we learned from this is that the sun and other natural effects are probably less than 15% of the changes that we've had in the last 100 years.
we sing. From the high rooftops down to the sea, no one's as dear as baby to me. Wee little fingers, eyes wide and bright, now sound asleep until morning light.